Chapter 5, Jitterbug World, Jitterbug Reality. My God, it's full of stars, said Arthur C. Clarke in 2010. The music of the spheres, the motions of the planet silently sweeping through space, the forces of celestial bodies touching the remote depths of the universe and moving forward. These are the beautiful images of classical science. By the time of the Roaring Twenties, physics had new pictures of reality, a world of Lilliputian solar systems with positive and negative bits of matter for suns and planets, darting and jumping specks by the trillions of trillions, forming the structures of everything everywhere. Atoms structured into crystal or disordered into glass, but always atoms in motion, in constant quaking nervous motion. And where the atom dance is frenzied enough, bonds yield and break, and atoms lose their pretense of structure, flowing off into liquid pools or gaseous atmospheres. Scientific study of this maelstrom of atomic activity has shown that matter has a wave-like nature, but the search for the source of this wave-like nature, however, has found nothing that could serve to underlie these waves. No pond on which there could be rippling waves that could be the particles themselves. All efforts to penetrate to an ultimate reality have yielded two mutually contradictory answers that must both be true. One, the ultimate reality is that matter consists of particles, not waves of energy. And two, the ultimate reality is that matter consists of waves of energy, not particles. Usually, when science or philosophy or religion, for that matter, makes statements that are internally inconsistent, reason demands that the claims be judged false. But in this case, the experimental evidence has been overwhelming. Matter presents both a wave-like and particle-like reality. Despite the clear inconsistency of such an interpretation of the experimental evidence, we are forced to recognize the fundamental truth of this duality, a truth that calls for an entirely new understanding of reality. The Matrix of Reality is the title of this next section. Resolution of the wave-particle duality problem, when it came, was less a response to Bohr's philosophic conundrum than a response to the need for a more accurate method for handling the problem of atomic structure. Like the puzzle of wave-particle duality they were to solve, two geniuses, Werner Heisenberg and Erwin Schrödinger, heralded the revolution in scientific thinking that brought quantum mechanics into being, with two entirely different solutions that seemed at first as impossibly contradictory as the original wave-particle paradox itself. In keeping with the ever-unfolding mystery of reality, their solution to the problem of wave-particle duality has created a new and deeper mystery that has come to be called cryptically the measurement problem. Heisenberg was born on December 5, 1901, in Würzburg, Germany. An interest in Bohr's planetary atom led him to study physics at the University of Göttingen, and then, in 1924, drew him to Copenhagen to study with Bohr at the university's Institute for Theoretical Physics. Drew him to Copenhagen to study with Bohr at the Universitet's Institute for, I assume this is theoretical physics, housed in a weird, rambling building that still suggests the ghost of its former glory may lurk somewhere within its odd, shadowy halls and narrow passageways. In 1925, while recovering from an attack of hay fever on Helgoland, an island in the North Sea, Heisenberg discovered a new and an exact way to find the discrete energy states of atomic systems. He discarded the method that had guided physicists to triumph after triumph for 200 years. He gave up entirely the idea of attempting to explain atomic objects in terms of models, mechanical pictures of objects and their interactions. For Heisenberg, there were only observations. What we know are only the events, the outcomes of our experiments that probe that other world, the microworld of the atom, and so our representation of that world should be a mechanics of observations. Heisenberg noticed that the discoveries of Planck, Einstein, and de Broglie implied a peculiar constraint on our effort to probe the world of the atom. To predict a particle's path, one must measure both its position now and its velocity now. Of course, when we measure either the position or the speed of an object, we do this by shining a light on the object or by sending some other beam of particles to illuminate its position so that we can get the numbers we need to calculate its future path. When we do this, however, we disturb the object a little. If the object is small, like an atom, an electron, or a molecule, such disturbances may be significant. This fact had long been known to classical physicists, but it was always assumed that a probe that would produce only a negligible disturbance would be used. Because, as Planck and Einstein had shown, light consists of discrete quanta, the best we can do in making the light dim is to use one photon to determine the position of an object. But even using only one photon, we cannot make measurements more accurate than about one wavelength. Remember that light is both particle and wave. To get accuracy in measurement on an atom's position requires photons with shorter wavelengths, photons with a higher frequency. But Planck and Einstein had shown that higher frequency photons have higher energies, and a higher energy means that the measurement will disturb the object's motion that much more. The more we try to find just where the particle is by using higher energy photons, the more we disturb the particle being observed. What's more, de Broglie had shown that what was true for light was also true for matter. Particles also have a wave-like character that limits any efforts to use electrons or other particles to find exact positions and exact velocities. There is an ultimate limit to the accuracy of the data we can hope to get by any means in order to determine the path of an object or to see the inner workings of the tiny components of our world. There are two lessons here. First, Heisenberg showed that if we take the uncertainty remaining in the most nearly perfect measurement of a particle's position, which we call a variation of or uncertainty, and x for the location of the object, and multiply that by the uncertainty remaining in the momentum of the object, this squiggly line, where again it means the variation in the value p, the object's momentum, we obtain a number that is about equal to Planck's constant. More simply put, there's a picture of this equation where this squiggly line means approximately equal to, and h is Planck's constant. This is Heisenberg's famous uncertainty relation. Nature sets rock-hard limits to our knowledge about the location and motion of things. That is the first lesson. Heisenberg's uncertainty relation is as widely known as it is misunderstood, however. The measurement disturbs things measured. that the observation of particles, people, and societies disturbs what we observe was already known, even if perhaps it was never of much concern before Heisenberg. But it is the second lesson, Heisenberg's second discovery about measurement, that is the real bombshell. Heisenberg pointed out that if there is a limit to the precision with which we can know an object's path, then to that extent, path has no meaning. We may picture in our mind that a photon goes this way or that, or an electron passes this slit or that. But if our imagination exceeds Heisenberg's limit, we are imagining a fantasy. Objects do not take a path in going from the event to a point A to the event at point B because path itself does not exist. Of course, when Heisenberg formulated this principle, it was a conjecture calculated and formalized by the equation we gave previously, but it was conjecture born of the insight of Heisenberg's genius and that has yielded a wonderful bounty of precise physical theory confirmed by experiment. What Heisenberg discovered was that the limits to our ability to observe the universe determines the boundaries of reality. Physical reality and observability are tied together. If you and I cannot observe it, it does not exist. Or is it perhaps, if it exists, it is because you and I observe it? Everywhere at once is what the next section here is called. Heisenberg showed that, contrary to our common sense conception of physical reality, the idea of path is neither fundamental to nature nor ultimately even a valid concept. It would seem that any effort to analyze the real world out there would compel us to use the idea of path as a basic ingredient of that analysis. When we talk about matter, we speak of the physical reality. The very concepts seem to cry out that one has to go from one place to another. An object must move position by position and thus describe some path. Surely it cannot be everywhere at once, here now and over there in the next moment, completely disjointed from where it was before, or nowhere one moment and back again in the next. How can one hope to construct, it might seem, completely from scratch, the whole of physics all over again and achieve a new understanding of motions of material bodies by throwing out this essential part of our conception of reality? But Heisenberg did it. In 1925, Heisenberg wrote, "In this paper, it will be attempted to secure foundations for a quantum theoretical mechanics which is exclusively based on relations between quantities which in principle are observable." That paper gave us the first formulation of quantum mechanics. In this new formulation, Heisenberg did not work with numbers that represented where an object was at a given time, which in the old classical mechanics would mean assuming that the object was located at a specific place. Instead, he worked with collections of numbers. At any time, the object could be in any place, represented by an infinite collection of numbers that tells us its possible locations. Conversely, if we were to look at any particular place, we might see the object go past at any time. To represent this reality calls for more than just a number. The complete idea of the location of the object calls for a whole array, a matrix of numbers. The same goes for an object's velocity or momentum. The object has an array of momenta, and it has an array of locations. In the new quantum mechanics, this matrices replace the old ideas of position and momentum. But if we forget about modeling the atom, which is something that exists only in our imagination anyway, and look instead at the facts of observation, we see not electrons with positions and momentum in given orbits, but photons that signal the relationship between orbits. What we know of the electron's position is in the jump it makes between orbits. Position actually is a relationship between one orbit and another. We do not know the coordinate x of the electron, but rather its transition from orbit 5 to orbit 1, from 9 to 3, from 14 to 2. These pairs of numbers represent positions in the matrix, the coordinate position. If we are able to look only at what we know from our observation of the radiated photon coming from the atom, must be a relationship between the set of orbits from which the electron jumped and the set of orbits into which the electron jumped. This gives us an array of numbers. This array is the matrix. And this matrix is the position of the electron in Heisenberg's new mechanics. All of this is true also for the idea of the velocity of the electron, or the idea of its momentum. Momentum now is not an absolute quantity. It has meaning only with respect to a measurement, and the only way to see it is as it expresses in the emission of a photon. Thus, momentum is also an array of numbers that represent possible orbital changes when a photon is emitted. Now let us see how Heisenberg's idea that there is no path actually works for atoms. To do this, we need to revisit classical physics for a moment. In classical physics, Newton's equations boil down to a prescription that tells us the path of an object. If we ask where an object goes, Newton's equation tells us where, when, and at what speed and at what momentum anywhere along the path. That location and that momentum go together to describe a point on the path. If the location is given, Newton's equations enable us to determine the path, and from that the momentum. And if we know the momentum, our knowledge of the path lets us find where the object is. But in the world of the atom, Heisenberg's uncertainty principle tells us that path does not exist. Given the position, there will be uncertainty about the momentum. Given the momentum, there will be uncertainty about the position. Heisenberg therefore proposed that there would be a difference between multiplying x times p and multiplying p times x. We must remember that x and p are no longer just simple numbers for the position and momentum of an object, as Newton had meant them to be, but that they are now arrays of numbers that tie the position of any beginning orbit of an electron to a final position on another orbit, and that tie beginning momentum to the final momentum. Heisenberg proposed that the difference between this equation here should be Planck's constant, h, that constant connecting the frequency of a photon to its energy. This is the same constant de Broglie used to determine the wavelength of matter waves, and it is the same number that Heisenberg used to express his uncertainty relation. One more thing should be mentioned about this new mechanics that Heisenberg proposed. He also said that this difference between this equation would be imaginary. He set the difference equal to IH, where I is the square root of -1, rather than to Planck's constant as such. The fact that there is an imaginary number in Heisenberg's equation is very important. The significance of its imaginary character may seem obscure at the moment, but we will come back to this later. For now, note that it does not mean the number does not exist, but rather in a sense that it exists as a potentiality to affect the things we see. Using this way of understanding the meaning of position, of coordinate locations of objects in the atomic world, and of describing their speeds and motions, Heisenberg was able to re-express the classical equations of motion, and to give them a new meaning in terms of arrays or matrices of possible locations and possible motions. His formulation does not follow the particle from one location to another, but rather creates an array of values representing all possible measurements resulting that might be found when a measurement is carried out on the object. It is as though the way in which an object gets from one place to another, from one energy to another, from one orientation to another, matters much less than the idea that eventually the object will be observed, and that when it is observed, it may be found in any one of a whole collection of possible states. Physics no longer describes where, but the potentiality of where, not how energetic, but the possibilities for an object's energy. In Heisenberg's case, the conception of reality had changed to a picture in which the things that actually are real are the measurement events. Things between observations become a bit fuzzier than they had ever been in physics. In a way, things not seen now become imaginary potentialities to affect what we will see. Within months of Heisenberg's discovery, Erwin Schrödinger came up with a totally different solution to the problem of reformulating all of physics so that it would account for the world of the atom. Schrödinger was born and reared in what cauldron of 20th century thinking, Vienna, Austria, in 1887. He began studying physics at the University of Vienna in 1906, and after receiving his doctorate remained until 1921 when he moved to Zurich. There, at the age of 39, he produced his great new formulation of physics. To note that his discovery would earn him a Nobel Prize risks trivializing the enormity of his achievement. Yet his new formulation was a strange child of his mind. It was something about which he would later say, "I don't like it, and I am sorry I ever had anything to do with it." We will see why shortly. Where Heisenberg used matrices, whole arrays of numbers, to represent the positions and the motions of an atomic particle, Schrödinger took de Broglie's conception of matter as waves and developed an equation that would describe matter exactly in terms of these waves. Where Heisenberg gave us matrix mechanics, Schrödinger gave us wave mechanics. The paradox of wave-particle duality gave rise to two paradoxical formulations of physics, one in which the discreteness of particles extended even into the description of space and motion as arrays of discrete numbers, and one in which everything was seen as waves. Incredibly, both gave the same accurate answers. If both Heisenberg's and Schrödinger's formulations give the same correct answers, then somehow underneath it all they must merely be different mathematical attire dressed up the same reality that each formulation only partly reveals. A year after Schrödinger developed his equation for wave mechanics, he showed that his theory and Heisenberg's matrix mechanics are basically the same. They are two special ways of talking about a much more general and much more abstract picture of reality that is described by something called Hilbert space, a world that is really an infinity of imaginary worlds. The next section is called Schrödinger's picture. Schrödinger's equation also described the diminutive world of the atom and the things of that remote microcosm. But it describes that world in a fashion that is totally different from either that of classical physics or that of Heisenberg. Whereas Heisenberg dispensed with the classical concepts that lay beyond what could be measured, the Schrödinger equation does the opposite. It introduces something entirely new. Schrödinger's equation introduces something that is a part of everything in this world, but something we have never seen or even suspected might exist. Schrödinger was looking for a wave motion to describe matter in a way that would be similar to the de Broglie matter waves. To do this, he introduced the idea of the height of this wave, or the wave function symbol, thinking that this is what matter is really made out of, the de Broglie waves. What he had really found was something quite different. Schrödinger found the wave equation describing the amplitude of matter waves, and he showed that this new equation agrees with Heisenberg's equations and with experiment. But if Schrödinger can be likened to a Columbus sailing a sea of mathematical physics, it was someone else, Max Born, who figured out where Schrödinger had gone and what he had discovered. Born showed that these matter waves are actually waves of probability. Schrödinger's wave equation is a formula that enables one to find the amplitude of these probability waves. It does not give probabilities directly. This, as we will see later, is of the most fundamental significance in our effort to discover the nature of reality. The next section is called the imaginary world of the quantum. Actually, wave equations in physics have always turned out to be formulas that are expressed in terms of the amplitude of the waves involved. For example, the equation for waves on the surface of a pond is expressed in terms of the height of the wave at any point above the average level of the pond's surface. Moreover, if one squares the amplitude and multiplies by some appropriate juggle factors, one obtains a number that gives the quantity of energy carried by the wave at that point. Adding this up for every point on the surface, that is, integrating the function over the surface, yields the total energy in the wave. Maxwell's equations, the ones Einstein judged to be so fundamental that he changed space and time to keep the speed of light constant, can also be expressed as wave equations, one for the electric field and one for the magnetic field. These are the equations for light waves, radio waves, microwaves, and so on. In these wave equations, the electric and magnetic fields appear as wave amplitudes. Again, if at any point we square the electric field and it to the square of the magnetic field at that point and multiply by the appropriate juggle factors, then we will obtain the energy density at that point in space. But if this electromagnetic wave actually contained only one photon, then the energy for the whole space would be the energy carried by this one photon. If we were to divide the answer by this energy, we would obtain an answer of unity, i.e., just the chance that the photon is somewhere in all space. Thus, the square of the electric and magnetic fields at any specific point simply gives us the probability of finding the proton at that particular point. As a result, the electric and magnetic fields for a photon are a kind of probability amplitude, just like the ones we use in quantum mechanics. That is the meaning of this new quantity that occurs in quantum mechanics. This matter wave that the physicists call the symbol wave function. But there are further things to discover about this strange new creature. In the case of the amplitude of a wave on the surface of a pond, one can actually measure the height of the wave. That is to say, one can directly measure the strength of the electric and magnetic fields in an electromagnetic wave, at least for low-frequency waves containing large numbers of photons. These are real quantities, as we mean the idea mathematically, but the Schrödinger wave equation contains an imaginary factor I, which is the imaginary number, the square root of -1. This I is a number that does not exist, but that multiplied by itself gives -1. Thus, wave function will always turn out to contain terms that are imaginary. That is, terms that are complex functions or quantities. Now, the fact that wave function contains imaginary terms does not really mean that it does not exist. We must be careful on this point. The complex character of the wave function in Schrodinger's wave equation means that what is there is a sense hidden from us. It means that what is there is a kind of potentiality. Let us say I have $1 million in the bank and I wish to build a store that costs $100 per square foot. For simplicity, let us talk about stores that must be as deep to store inventory, say, as they are broad across the front. Obviously, then, my $1 million is enough to buy a store with 100 feet of frontage. Now, let us say that I had a bad week at the stock exchange and lost $250,000. That would still leave enough money for a store 87 feet wide. But what about the lost money? What is the length of the storefront that I lost? If I had that $250,000, I could use it to build a store with a 50-foot front. But because this is a money deficit, I should talk about the imaginary 50-foot storefront that is a 50-I-foot storefront. I will never see a 50-I-foot store, of course, but that lack of money will affect the look and size of the store that I do finally build. Tongue-in-cheek, a mathematician might say that what I have left after losing $250,000 is a building 100 plus 50 feet wide. In the same way, incredibly, matter can have an imaginary existence. It can exist as though money were short at the bank. There is an imaginary aspect to these quantum mechanical waves that we must remember, but we must also be careful when we speak of these imaginary numbers as not real. Both mathematicians and physicists are inclined to view such an understanding as naive. The mathematician's imaginary is not the layperson's imaginary. Still, the observable quantities, those things that we can measure or see and that are described by wave functions, are always obtained from that function by a procedure that turns these imaginary numbers into real numbers. We can talk about the 100 plus 50 foot wide building, but when we build, we will be putting up a 7,500 square foot building. It is that actual floor space that we finally build. It is easy to look at this emptiness, this wisp of motion in a relative space, and understand how memories vanish with the years. There is so little of us even now. We are such small creations, and there is so much emptiness ahead of us, so much emptiness in so many years that it is surprising that I hear now any echo at all of her voice, and that is stranger still that something so slight as feeling should have endured. She had pride in her name, pride that her name was special. I remember her showing me how to spell her name with an E, Marilyn, not Marilyn. She was a special creation, unique. Her lips were full and red, the bright red of the 50s. She did not like seamless stockings. They lacked that touch of excitement. She wore stockings with dark seams that had to be kept straight up the back of her legs, like racing stripes painted on a fast car piping out its sexiest curves. She was alive, vital, vibrant. There was something that the rest of creation, whether stars or atoms, could not be, something that once lost could never be made again. She loved her mother and respected her stepfather, but she kept her real father's name. She remained Marilyn Ann Zender, honoring and cherishing the memory of her father. She kept his name to keep his memory alive, just as I try to keep something of her alive through my memory of her. Yet where is the reality of any of this? Ralph, her stepfather, carries a photograph of her in his wallet with him to this day. Ralph is old now. He has been retired for many years, but Marilyn is 16. She still has a gardenia pinned in her brunette hair. The white petals of that flower complement her own petal-like skin. The gardenia is so delicate that if one touches a petal, the petal turns brown. I remember her skin with brown blotches as she lay dying in the hospital. Marilyn and the gardenia, two southern flowers, delicate and beautiful. Memories of long ago. What resemblance does this description of physical reality bear to the woman I knew then? My feelings are strained by the thought that these strewn speckles of atomic matter, this dust of particles fixed in a void, that this empty structure could ever be all that there was to the verve of her glance. What relationship can there be between this story of atoms giggling at 10 hertz squared by 15, 10 to the 15th power, and the etherless void of twisted time and space, and her languid smile, her breath breathed near me, her lips touching, slowly touching my own? If these are two different stories, the one of atoms and particles, the other of this image of her, one must be a fable. And yet there is another side to this story, one that is filled with the excitement of ideas themselves, ideas that let us piece together what our reality is through layer after layer of mechanism. It is this mechanism that shows the workings of atoms that, when put together, make up bits of organic macromolecules, in turn combined into the materials that form flesh, bone, muscle, nerves, and skin. It is this mechanism that brings movement to bodies, enlivened by the neural networks and the brain. All these factors of science let us understand how these things work. As much as it seems that these two worlds cannot be bridged, this story of science works too well at each level for it not to be true. Each mechanism at each level of the story folds so well into the next. These are the stories of atoms formed into molecules, of molecular reactions and conformational changes, of chemical kinetics forming, shaping, and moving the structures of the cells. These are the stories of how photons, encountering the scarce electrons in atomic structures, re-radiate light that enters my eye and cascades into a neural response that travels down the optic nerve into my brain, sending impulses that represent the shapes and patterns of her body. And then these impulses become a memory. All of this works so well, yet why is it that I feel that I had to bring the existence of those atoms into some contact with my own brain's activity for me to be able to justify that those atoms and Marilyn could have ever been part of the same story? The lesson is that the atoms themselves never form tissue, never form the woman. The atoms are atoms. They are not parts in themselves. Only because I see the woman and feel her, and only because I know of the atoms, are they the parts of something that I build in my mind and can imagine is she. I remember one day long ago, I rather nervously rang the bell. I always rather nervously ring the bell. I never knew whether her mother or stepfather might answer the door, and I always felt more as though I had come to steal something than simply to visit their daughter. Of course I had. I had come to steal her away, and there was no way to hide it. I was sure they must feel I was the thief in the night as far as their daughter was concerned. Her stepfather was a tall, strong steel worker. Her mother was small, like Marilyn, except for their difference in age. might have been her twin. Both her parents were always pleasant to me, but I knew it was a veneer, a thin, brittle, transparent sheet of mica. I rang the bell and Marilyn opened the door. Quietly, I slipped in. "Where's your mother?" "You want to see my mother?" she asked. "No, just wondering." I always started by checking the logistics. I always hoped we would be alone, of course, but that was unlikely. I just wanted to know through which door one of them might suddenly appear. Whichever direction it was, I would always listen intently for the first sound of footsteps and any unexpected squeak of the flooring. "She's in the kitchen making us some cookies. You want some? We can have some later if you want." This concession to Southern hospitality did not alter the terms of my visit. At best, I could feel only about as welcome as the Japanese fleet off Oahu. I was shown into the living room as usual. I remember the thick carpet covering the whole floor. My parents' house was carpeted in the living room too, but this carpet seemed to quiet the whole world. It was heavy and soft. The living room was perhaps 12 feet wide and 20 feet long across the right front of the house. Marilyn usually showed me to an upholstered chair just inside the living room, a chair reserved for the man of the house. There was a picture window to my left, a fireplace that was never used on my right opposite the window, and always beside me Marilyn, who would sit on the arm of the chair on the floor in front of me or with me in the chair. When I knew her better, there was always a kiss for me when I came in, and perhaps a second. I would usually go over to that man of the house chair, sit down, and motion for her to join me. She would sit on the arm of the chair, lean across the front of me, as if about to kiss me, pause and look at me. "Did you miss me?" I would ask. "Did you miss me?" she would demand. "I asked you first. Did you miss me?" "Yes." She was soft and warm toward me. For her, the games quickly ended. "I missed you too," I would say. "How much?" Once I held up my hand, I remember, thumb and forefinger showing a gap of about a quarter of an inch. "That much," I said. "That's not much," she answered. I grabbed her shoulders, pulled her close, and said, "There is an infinity of points between, and space enough to slip the sun through." We were, after all, foolishly young. This was the best my youthful mind, adrift in its newfound land of love and poetry and science, could do. A quote from something I had just read in mathematics for the millions. "Do you like Seal?" she asked. Ceil. "She's okay, I guess. I don't know why. I think she's got a crush on you." Seal was her friend, but the statement was couched as if she were an expendable commodity. "I don't like Seal. She doesn't mean anything to me. She's just been coming by a lot more since you've been around. I think she's got a crush on you." She smiled, pleased, as a woman will be when she knows she has someone another woman would like to have. "I don't care. She doesn't mean anything to me." I didn't say any more. I pulled her an inch closer and kissed her. This next section is called Orthogonality and Other Things That Go Bump in the Night. Orthogonality, Orthogonality. Let us see how this quantity wave function symbol that comes out of Schrödinger's theory is used to obtain actual probabilities. To obtain the probability that an electron in an atom can be found in a particular volume located, for example, close to the nucleus of the atom, we first solve the Schrödinger equation for the problem. That is, we describe mathematically the collection of particles and forces that interact in the atom on the electron. This is put into the Schrödinger equation. Then we carry out the math needed to obtain the wave function free and clear. That is, to get the results in the form wave function equals whatever. If we specify a particular location in space and put the numbers for that location into the formula for Schrödinger's wave amplitude, wave function, symbol, then it becomes simply a number, the value for the wave function at that location. But that number is a complex number made up of a real part, R, and then an imaginary part, I, S, where again I represents the imaginary factor. Thus the value of wave function is R plus IS at the specified location. Because wave function is a complex number, it is awkward and difficult to understand. It is like that store we built in the preceding section that had $250,000 of lost frontage, just as there, where it made more sense when we talked about the actual square feet of floor area in the store, here too wave function was more meaning in terms of numbers and in terms of what it represents when we talk about the quantity when it is squared. Squaring wave function, if it is done right, gets rid of the imaginary part of the number. Mathematicians and physicists show that they know how to square the thing by writing the symbol for this square. When we square the magnitude of wave function, we get something useful. It is called the probability density. It enables us to find the probability point by point in the region around the atom. Thus, the probability P of finding the electron in a small volume near the nucleus of the atom will be the square of wave function multiplied by the volume of space we are talking about. To make it clear that the volume has to be kept very small, or the value of a wave function will change from one side of the volume to the other, we write dV rather than just V for the volume. The expression for the probability of finding the electron in the volume dV is then just this equation. If we do all the algebra, we get R squared minus S squared dV for the probability of finding the particle in the volume dV. If we want to get the probability for finding the electron in a larger volume, then we have to add up all the little pieces for all the little dV volumes throughout the larger volume we are interested in. Now let us see what we have. Here, R squared is like the number of square feet that the $1 million could buy, while the negative S squared is the 250,000 in store space that was lost. When we get down to any real business about the electron, we have to talk about this quantity, which says that the probability that we will find the electron in the little volume of space dV is obtained from the squares of the real and the imaginary parts of the wave function. It is as though we had a new kind of electromagnetic field in which the magnetic part competes with the electric contribution rather than adding to it. But this probability wave function is stranger even than merely being made out of imaginary parts. It is not only a probability wave, but it is at the same time the complete representation of any object or physical system for which it has been obtained as the solution to the Schrödinger equation. This latter fact was originally postulated by Bohr, when it has been exhaustively verified. Wave function turns out to describe not only the probability for something happening, but it describes also exactly what can happen. Not only does it describe the electron probability distribution in the atom, it provides all the information for all the possible things that can happen, all the possible configurations, all the possible orbits, all the information needed to find the energy of the electron or the momentum or how it will interact with the photon that strikes the atom. How is this all contained in one function? It happens that the Schrödinger equation yields solutions to a very special type, These solutions can be expressed in a series of functions that is a series of pictures of the atom that can be written in this particular form, an equation or of waveform. Each of these quantities, wave function 1, wave function 2, wave function 3, etc., is like a photograph that pictures each possible state. Each is a mathematical picture of the electron in its particular orbit or special configuration in the atom, each with its own particular energy for that configuration. And like a photograph, which can be under or overexposed, each of these quantities can show the probability for its occurrence by means of a multiplier, a coefficient that is smaller or larger depending on the probability for that picture becoming the reality we find when we look. All of this can be found by solving Schrodinger's equation. Thus, the whole procedure for finding the permitted configurations that the atom or the system can be in, as well as the chance for finding it that way, is given in a straightforward way by the Schrödinger equation. The wave function is the description of all the possibilities, all the allowed configurations of that atom simultaneously. This wave function of Schrödinger's equation, containing these simultaneous pictures of all possible configurations, gives us what is called a linear superposition of states. This means, first of all, that these individual states or pictures of the atom are simply added together, and second, that this superposition still manages to keep the separate parts separate. This is the property called orthogonality. It means that at the same time, the wave function 1 picture exists as a true picture of the atom, the wave function 2 picture also exists along with it, as does the wave function 3 picture, and as do all the other equally valid pictures of the possible configurations of the atom. To understand this better, imagine that we have a transparent cube, and on each of the three sides of the one corner, we paste a photograph of each of these three wave function 1, 2, and 3 pictures. By turning the cube, we can see front on one, but only one on the 3 pictures fully without distortion. That is what the term orthogonality means. If we calculate the extent to which the atom can be found to be in both the first configuration and at the same time in the second configuration, we get 0. These two states are perpendicular or orthogonal to one another. The object can never actually be seen in both states, but is in both as a potentiality. If on measurement, however, it is found to be in the first, then the second will become just a bump in the night that never was. 2 more points and we will be done. In the example of the cube with pictures pasted on, we can do this with only 3 pictures. That is because we live in a world limited to 3 dimensions. Using mathematics, it is possible to do this with more pictures, and even with an infinite number of pictures all at once. Also, we have to note that when we turn the cube slightly, we can see 2 or even all 3 of the pictures fairly well. But if instead the cube were under the surface of some murky water, then turning the cube could bring only one of the pictures up, even with the water's surface. In that case, we would not see the picture until it was even with the surface, and the other pictures would not be visible at all. That is how it really works. That murky water world is like the imaginary quantity that appears in the mathematical expression. Rotating the cube is the same as rotating the mathematical function out of the imaginary space. It lets the function become real so that we can see an image. This is something like the process of measurement or of observation, something we will be particularly concerned with later on. To sum this all up, the wave function, that we get from the Schrodinger equation packs in a whole lot of information that amounts to an infinite number of pictures of what the atom really is all at once. This next section is called the hop, pop, jump quantum world. Matter is not really both particle and wave, but rather discrete packages of energy that dart from place to place in a frenzy of quantum jumps that ebb and flow in waves of chance. It is a world in which nothing stays long where it should be, but only stays where it could be. The atoms dance and the electrons hop, zipping about from the wildly random thermal commotion and from the blurry speed with which probability waves speckle the tiny electrons around their nuclei, painting fleeting mazes into solid things like you and me and her. And yet none of this is what is there. All of this motion is frozen. All this darting and all these quantum jumps exist only as potentialities. The jumps and darts happen when measurements take place, when we observe, and when things interact with other things. We cannot view the probability waves as arising because real discrete particles of matter in precise locations with exact speeds dart about so fast or so discontinuously that we cannot follow their true paths. They have no path. They have no exact place and no exact momentum. They exist as potentialities at all these places at once, a frozen static frenzy, the silent excitement of nature. Particles do exist, but their states are represented by waves of probabilities. That is the resolution of the wave-particle duality paradox. That is the solution that cloaks still more mysteries than we ever thought might hide there. End of chapter.